Now we have to discuss about collision. Collision is a very important phenomenon which we will understand by using law of conservation of momentum and law of conservation of energy. So collision is basically of two kinds, elastic and inelastic. We will see the elastic and inelastic collision over here, and then we will consider the one more classification, that is head-on and oblique collision. So right now I will be discussing with you elastic, what is elastic collision or what is inelastic collision. So let me consider a case. Suppose you have a body of, say, mass m1 moving with velocity v1, and you have a body of mass m2 moving with velocity v2. This is the case before collision. This is the case before collision. Now you have, suppose v1, suppose if v1 is greater than v2, then a time will come, the distance between them is going to fall. If v1 is greater than v2, the separation between the two bodies are going to fall, and then a time will come when they will collide. This m1 is going to hit m2 from the back, right? This is m1 and this is m2. m1 is going to hit m2, right? When it hits m2, see what happens. When it hits m2, then m2 exert a force on m1 and m1 exert force on m2. I'll show the diagram over here. This is a reaction, impulsive force. m2 exert impulsive force on m1 and m1 exert impulsive force on m2, right? This is n. m2 exert force n on m1, m1 exert a force n on m2. The action reaction pair, these are impulsive forces. They act for very small time and very high in magnitude. They are very high in magnitude, right? This is the case during collision. This is the case during collision. And as a result of these impulsive forces, m1 starts traveling with v1 dash and m2 starts moving with v2 dash. m1 starts moving with v1 dash and m2 starts moving with v2 dash, right? This impulsive force is going to slow down m1, and this impulsive force n is going to make m2 faster. v2 dash will be greater than v2 and v1 dash is smaller than v1, right? So in this way, this impulsive force will decrease the velocity of m1, it will reduce the momentum of m1, and this impulsive force is going to increase the momentum of m2. Meaning, I can say, if suppose this impulsive force acts for a very small time, then in this small time, this n dt, n is towards left, so I write minus n. This is n is towards left. In left direction, if I take negative, and right direction, I take the force as positive, then minus n dt equals to m1 v1 dash minus m1 v1. This is impulse. Impulse is changing momentum. When this n acts for a small time, it creates an impulse. It creates a change in momentum. Whereas n dt acting on m2 is going to, this n acts towards right, so I have taken it as positive. So that should be equal to m2 v2 dash minus m2 v2, right? m2 v2 dash minus m2 v2. So if you see this case, what happens? This plus this, or you can say this is negative of this, right? I can write m2 v2 dash minus m2 v2 is minus of m1 v1 dash minus m1 v1. That is the final momentum. This is m2 v2 dash plus, or you can say m2 v2 dash this will come this side, that is m1 v1 dash is equal to m1 v1 plus m2 v2, right? This is one equation that you are getting. What is this actually? This is the linear momentum of the system after collision. This is a linear momentum of the system before collision. System of what? System of these two masses. System of these two masses. And why they are getting conserved? Because there is no external force acting on the system of these two bodies. The only force is N, which is internal force. N is an internal force. This is not external force. There is no external force acting on the body. So linear momentum is getting conserved. Linear momentum is getting conserved. This is nothing but conservation of linear momentum. This is conservation of linear momentum. So linear momentum is getting conserved. Whatever momentum is lost by m1, equal amount of momentum is gained by m2. So when they are colliding, they are interchanging, they are sharing, they are transferring momentum to each other. m1 is transferring momentum to m2. Momentum of m1 is falling, momentum of m2 is increasing. So m1 is giving some momentum to m2, right? And so m2 gains momentum, m1 loses momentum, and the amount of momentum lost by m1 is equal to the amount of momentum gained by m2. And that's why you are finding that the linear momentum of the system as a whole is remaining constant, right? The linear momentum as a whole is remaining constant. These two particles are interacting among themselves. When the particles interact among themselves, they share momentum, but the momentum of the system remains same. So that's this equation is coming from law of conservation of momentum. What about law of conservation of mechanical energy? What about energy? So here I'll be talking only of mechanical energy because we are talking about energy conservation in a classical system. So classical energies are of two types. Energy of the classical system, which is called mechanical energy, are of two kinds. That is M1, that is energy possessed by these particles are of two types. One is potential energy, other is kinetic energy. In this collision, I am not considering any change in potential energy. This is a horizontal plane, so the gravitational P is remaining constant throughout for every particle. And second thing, I am considering these two particles as a hard ball. They are very hard ball, so they are not getting deformed as well, right? So there is no change in the potential energy, but when they collide, you may have a part of kinetic energy getting converted into some non-mechanical form of energy like heat, light or sound. When the two bodies collide, practically a part of kinetic energy gets converted into heat, light and sound. When you have two particles colliding with each other, you will find those two bodies becomes hot, right? And sound is also produced. Sometimes when the two particles collide very hard, light is also produced, right? So the big question is, from where these energies are coming? These energies are obviously coming from kinetic energy. This energy cannot appear out of nowhere. The energy, if it is appearing, it must be coming from somewhere. So when this heat, light and sound is produced, a part of K is getting transformed into these energies. You may have an ideal case where none of the K is getting converted and the K before collision is equal to K after collision. This is the case after collision. So in general, what I can write is, in general I can write m1 v1 dash square plus m2 v2 dash square is less than equal to half m1 v1 square plus half m2 v2 square. This is coming from law of conservation of energy. If energy is conserved, K is not getting lost, there will be equality over here. If some part of K is getting converted to heat, light or sound, this final K will be less than initial K. So these are the equation 1 and 2 in general, right? When there is no conversion of kinetic energy in heat, light and sound, it will be equality. If there is some conversion of K is getting converted to heat, light and sound, then I'll call it less than, right? I'll put less than sign over here. Now I can transform this equation into, I can write m2 v2 dash minus m2 v2 dash minus v2 and m1 v1 minus v1 dash, I can call it 3, and I'll cancel all these equations, all these halves, and I can write m2 v2 square is less than equal to m2 v1 square minus v1 dash square. Now v2 dash is obviously greater than v2, v1 is greater than v1 dash. So if I take the division, I'll write v2 dash plus v2 is less than v1 dash, or I can write v2 dash minus v1 dash, or I should write less than equal to v1 minus v2, or v2 dash minus v1 dash is v1 minus v2 less than 1, less than 1. So how much this will be less than 1? When do you have this ratio getting equal to 1? This ratio is equal to 1 when there is no conversion of kinetic energy into heat, light or sound. When mechanical energy is conserved, this ratio is equal to 1, right? When there is a part of kinetic energy is getting converted into heat, light or sound, then this ratio becomes less than 1. And how much this ratio becomes less than 1 will depend on how much kinetic energy is getting converted into non-mechanical form. How much K is getting converted into heat, light or sound. This ratio is less than 1, and how much it will be less than 1 will depend on what amount of K is getting converted into other form of energy. If suppose this is 0.99, I can say a very small part of K has got converted into heat, light or sound. See, this is not the ratio, which tells you the percentage of K getting converted into heat, light or sound. Remember, if it is 0.95, it does not mean 5% of the K is getting converted into heat. No, it's not. But it gives you some idea about the fraction of K. It gives you some idea. Really, it gives you some idea. It gives you a good idea of how much K is getting converted. If it is 0.95, we can have an idea that only a small part of K is getting converted into heat. If it is 0.1, then I can have a large part. I can have an idea a large part of K is getting converted into heat. It's not like 90%. It's like large part of K, right? So this ratio is extremely important. This ratio is extremely important because this tells you, this gives you an idea about the nature of collision. Nature of collision. If this is 1, there is no transformation of K, energy is getting conserved, mechanical energy is getting conserved. If it is less than 1, it means a part of K is getting converted into heat, light or sound. That's why the ratio is very, very important. In one shot, it is giving you an idea, a good idea of the collision. So this ratio is called coefficient of restitution. We call it coefficient of restitution. This ratio is called coefficient of restitution, which is denoted by E. So we write coefficient of restitution E as V2 dash minus V1 dash V1 minus V2, which is nothing but this is the velocity with which the two particles are getting separated. See, the difference in the velocity, if this minus this, is giving an idea with what rate the separation is increasing. With what rate the separation of the two particles is increasing. Whereas V1 minus V2 is giving you an idea with what rate the separation is falling. With what rate the two bodies are approaching each other. This is giving an idea with what velocity the two particles are getting separated from each other. So this is velocity of separation upon velocity of approach. This is velocity of separation upon velocity of approach. This is velocity of separation upon velocity of approach. You just remember this. You can remember it. You just put it like V2 minus V1, right? So this ratio is very, very important, and this ratio is 1. It means mechanical energy is completely conserved, and the collision is called elastic collision. We call it elastic collision. So there is nothing called perfectly elastic. Perfectly elastic means elastic only. If E is equal to 1, E cannot be equal to 1 in more than one way, right? So it is elastic. It's not like perfectly elastic, it means elastic only, right? If E is less than 1, then it is called inelastic collision. It means a part of K is getting converted into non-mechanical form. So it is inelastic collision. Inelastic collision. When E is equal to 0, what does it mean? When do you think E can become 0? E can become 0 when this numerator is 0. When this numerator is 0 means what? If V2 dash equal to V1 dash, it means the two body, when they collide, the velocity changes to V1 dash and V2 dash. These velocities are equal. When these velocities are equal, it means the two body do not get separated. They do not get separated. Velocity of separation is 0. The two body will be moving with the same velocity. They collide, they come together, and they have the same velocity after collision, so they do not get separated. They come together and remain together, right? So some people call it they stick to each other. Actually, they do not stick to each other. They remain together. There is no gum and which is sticking them together. No, they remain together. Since the velocity after collision remains same, they are not getting separated. They remain together, and that's called perfectly inelastic collision. We call it perfectly inelastic collision, right? So in fact, we come across two equations. One is M2V2 dash, write it. One you are getting from conservation of linear momentum, V1 dash equals to, or I should write simply M1 V1 dash plus equals to M1 V1 plus M2 V2. And the second equation we are getting from here, V2 dash minus V1 dash. I can write V2 dash minus V1 dash equals to E of V1 minus E of V2, right? E of V1 minus E of V2. This is fifth and this is sixth. So from here I can get V2 dash and V1 dash. So what I can do over here, tell me, how will I get V2 dash? If I multiply the sixth equation by M1, I'll get M1 V2 dash, M1 V1 dash, EM1 V1 minus EM1 V2. This is our, sorry, I don't write anything. This is, let's say, seventh equation. And if I add 5 plus 7, then we are getting, this will cancel out, and you will get 2, or I should write M1 plus M2. So that becomes, I can write M1 1 plus E V1 and M2 EM1 V2, right? So I can write V2 dash as 1 plus E M1 V1 M1 plus M2 plus m2 minus em1 v2, right? v2. Okay, so that's the velocity of second body after collision. How can we find the velocity of the first body after collision? I can do it over here itself. See, if I multiply, say, m2 to the sixth equation. If I multiply m2 to the sixth equation, this is m2 v2, m2 v1 dash, em2 v1, and em2 v2. This is eighth equation. And what I can do is I can add I can subtract fifth and eighth equation. That will give me what? That will give me m1 plus m2 v1 dash, and this will give you m1 minus em2 v1 and m2, sorry, what should I write? Take m2 plus em2 v1, or your v1 dash is coming out to be m1 em2 v1 plus I write 1 plus e m2 v2 m1 plus m2. Alright, write v2 over here, v2, right? So that's your v1 dash and v2 dash, v1 dash and v2 dash. For elastic collision, your E is 1, so your v2 dash becomes, please check, I'm not sure, I don't remember this formula, right? I've done it before you itself. So v2 dash is, or I like v1 dash is, v1 dash becomes, if I put E equal to 1, this is m1 minus m2 upon m1 plus m2 v1 and 2m2 m1 plus m2 v2, and v2 dash is, I can write 2m1 v1 m1 plus m2 what should I write, v1 plus m2 minus m1 plus m2 into v2. And for perfectly inelastic collision, we know that v1 dash and v2 dash are equal, so that will check my result whether I got right result or not. Inelastic collision E is 0, so that should give me what? v1 dash equals to m1 plus m2 v1 plus m2 plus m2 v2, and v2 dash will give me m1, oh, I'm getting right result, m2, that's fine. We are finding that v1 dash is v2 dash. I hope my result is correct, right? I can hope my result is correct. Okay, so these are the results. There can be some special cases which I can get. Say if m2 is at rest, if m2 is at rest, and say m2 is much larger compared to m1, like I throw my ball on the wall. If I throw my ball on the wall, what do I expect? The wall is very heavy, it is at rest, So what should I expect? If it is elastic, what should I expect? I'll put it over here. V1 dash is, see, or I'm saying V2 is 0, and so my answer is M1 minus M2, M1 plus M2 V1, and then what I can write is M1 by M2 minus 1, M1 by M2 plus 1 into V1, and that's going to be 0 if M2 is very large compared to M1. So I'm getting V1 dash is V1, right? And so what do I expect for V2 dash? Do your wall move? When you throw the ball on the wall, does it move? Can you tell me? Have you ever tried? If you throw the ball on the wall, does it move? It doesn't move. So my result should give you that V2 dash should be 0. That let's see. Let's see that 2m1 v1, and that is 2m1 by m2 upon m1 by m2 plus 1 v1, and that gives me 0. V2 dash is 0. Okay. So v1 dash is v1 minus v1 and v2 dash is 0. Wall doesn't move. The ball rebounds. Ball come back with the same velocity and come to your hand. That's elastic collision. That's the case of elastic collision. Now I have one more beautiful case. If suppose m1 is equal to m2 and m2 is at rest, what should I expect? Have you played a carom board? If you strike when you're one of the, one of the disc, right? I don't know the exact word. So if one of your disc strike the other disc, what do you expect? The body which are moving will come at rest, and the body to strike starts moving. Have you ever seen it? The body which was moving comes at rest, and the body to strikes start moving. M2 was at rest, M1 is equal to M2, M1 was moving, it strike M2. So it means they are interchanging the velocities. If I put it over here, I'll get the thing. They are interchanging the velocities. See, I can just put over here M1 equals to M2. So what do you get? V1 dash is 0 and V2 dash is what? If M1 equals to M2, V2 dash is V1. It means when M1 was moving with V1, M1 comes at rest and M2 which was at rest start moving with the same velocity as V1, right? So they interchange the velocities. That's a good case. That's a beautiful case, right? So this is how we can discuss. This is all about elastic and inelastic collision. This is about elastic and inelastic collision. You can remember this formula, right? You can remember this. So this is all about elastic and inelastic collision. All right. Thank you very much. So we have the good idea of what are the velocities after collision, right? Say this is I can write this as V1, this is V2, this is 90 degree. So this velocity theta. Now I can conserve linear momentum of body number 1. I can conserve linear momentum of body number 1 in x direction, A alone. I can generate some equation. A alone. So in x direction, the momentum of A before collision was mu sin theta, and that will be mv1 cos theta. The momentum of B alone in x direction is, it was 0 initially, finally also it is 0. Okay. A plus B as a system, we can conserve momentum in y direction. That is, initially it was mu cos theta, and finally it will be mv1. I can write v1 sin theta, but that is in negative y direction. So minus mv1 sin theta plus mv2, and I can get one more equation from E, that is the second body is v2 and v1 dash is I am interested in the velocity component after collision along the line of force. So that is v1 sin theta in negative y direction. So minus v1 sin theta in negative y direction. v2 is 0 initially and v1 is u cos theta. I am only interested in the velocity component along the line of force. So I am getting here from here v1. v1 is u tan theta, and from here I am getting v2 mv2. So from here I generate one equation, that is v2 plus v1 sin theta equals to u cos theta. u cos theta. So if I multiply by mv2, that is mv1 sin theta, mu or emu cos theta. Okay, so this can be written as mv2 from here is mu cos theta plus mv1 sin theta. So I can put it here, mv2 as mu cos theta. So you are free to solve in your own way. Now what I am doing is not physics, it is just mathematics, right? So you do your own steps, don't follow my steps. You can do it yourself. Okay, so I need this result, no? I need this result, so that will come automatically. So what we are getting is, we are getting I have v1 with me. I have v1 is u tan theta, so that becomes mv1 sin theta tan theta. Oh sorry, this is u tan theta. v1 is u tan theta, so mu tan theta sin theta and mu tan theta sin theta is emu cos theta. Okay, so I'll take this on the side. So this becomes what should I write? M plus m. I will take this side. M plus m u tan theta sin theta is em minus m u cos theta. U and u will cancel out. If I bring cos theta this side, it becomes tan square theta as em minus m plus m, and I think that is exactly what we had to prove. Yes, this was exactly what we had to prove. This is your answer. So this way you can do that. This is the way you can do that, right? So this is a good problem on oblique collision. Similarly, you can do any problem on oblique collision. Getting my point? Okay, I hope it's clear. This is the approach. Just follow this approach. I don't think that you won't be able to solve any problem. You can solve any problem, in fact, right? You'll be solving every problem. Follow this approach. Okay, if you come across any problem which you don't solve,